Hello and welcome to the part 3 in the series of videos on diffusion models. I am Dheeraj, and we'll again try to rederive an expression for the evidence lower bound for variational diffusion models, and we'll see how it leads to an efficient method for training. So in the last video, we saw that one way of splitting the ELBO term gave us three types of terms. One was the prior matching term, which did not have any parameters. The second was this consistency term, wherein we tried to match the distribution of xt from likelihood, that is given xt plus 1, and the posterior, that is given xt minus 1. Here we saw that this requires an expectation over three random variables. So if we perform it using Monte Carlo sampling, this this average is going to have a very high variance, although it's still an unbiased estimator. And finally, we had a third term, which was the reconstruction term. The problem is with the set of consistency terms, and the issue comes up because in the numerator we have xt conditioned on xt plus 1, whereas in the denominator we have xt conditioned on xt minus 1. As a result, we need to take average over three latent variables, xt minus 1 and xt plus 1, right? Now, how do we eliminate this sort of problem, right? And so we'll see that in today's video. So the solution to the previous problem is that we'll have to flip the order of variables in xt given xt minus 1. The reason is that if both the numerators and denominators have xt conditioned on the same latent variable, then it will be easy to perform this expectation, because then we'll have the same set of two variables over which we need to compute the expectation. So the idea is that we need to flip the order of variables in q xt given xt minus 1 using Bayes rule, right? So using this Bayes rule, we need to flip the order of variables over here. Okay. Now the thing is that so firstly, if we try to apply the Bayes rule, then essentially we'll get the terms of the form of so as we'll see, if we try to apply the Bayes rule over here directly, right? So what do we get? So if we try to model this, we are going to get xt minus 1 over q of xt minus 1. Right? But now this is an ill-defined expression. The reason being that the posterior distribution is only defined when conditioned on x naught, right? If you have xt minus 1 already, then you don't need to condition on x naught because even if I condition it on x naught, it's already the form of the distribution is not going to change because of Markovian property. But otherwise, for example, just this qxt minus 1, right? So this is not going to be well defined in general. Similarly, the numerator is also not going to be well defined in general. So in order to flip the order of latent variables, we first introduce x naught. So we write xt given xt minus 1 as xt given xt minus 1 and x naught. Okay. And now we can write it as q of xt comma xt minus 1 given x naught over q of just xt minus 1 given x naught. Okay. Now we look at the numerator. So we write this expression as q of xt given x naught times q of xt minus 1 given xt and x naught over q of xt minus 1 given x naught, right? So this is true for all t greater than equal to 2, right? Because for t equals 1, actually we cannot flip the order because it's just q of x1 given x naught. For t greater than equal to 2, we can flip the order in this manner. Now let's take a look again at the evidence lower bound. So what we had was that this log px, this evidence lower bound, was this expectation of q of x1 to capital T given x naught and then I had log of pxt times product of t from 1 to capital T, p theta t, xt minus 1 given xt, right? And in denominator I had product of t from 1 to capital T, q of xt given xt minus 1. Okay, and the idea is that if we take this term in the denominator, okay, and what I then try to do is that I try to apply base rule here for all t greater than equal to 2. So firstly I take out the x1 given x0 term from this expression. So I have expectation of q of x1 to t given x0 log of pxt product of t from 1 to capital T, p theta t, this is small t, xt minus 1 given xt over q of x1 given x0 times the product of t from 2 to capital T, q of xt given x0 times q of xt minus 1 given xt and x0 and over q of xt minus 1 given x0. Okay, so now I can write this as expectation over q of x1 to capital T given x0 of log of p x capital T plus sum over t from 2 to capital T log p theta t xt minus 1 given xt over q of xt minus 1 given xt and x0, okay, plus log of 1 over q x capital T given x0 plus log of p x0 given x1. Okay, so what have we done is that if we look the expression here, so firstly this pxt we took outside, okay, and now the thing is that this xt minus 1 given xt, okay, so we started so from t equals 2 onwards, okay, we started combining it with this xt minus 1 given xt and x0, right, from 2 onwards. For t equals 1, what I have is log of p x0 given x1, which I have taken out separately, okay, and now if you look at these terms, q of x1 given x0 and this product of t from 2 to capital T, q of xt minus 1 given x0 and this q of xt given x0. So all these terms, so just work it out, all these three terms, right, this product and this qx1 given x0, they'll all cancel with each other in the end, and what you will be left with is just 1 over q x capital T given x0. Okay, so just this x capital T given x0 will remain, right, and there is a log of 1 over qx capital T given x0, right. So just verify this calculation yourself and you will see that this expression does hold true, right. And now what I do is that I just combine these two terms again, okay. So what I'm going to get is that, so there is an expectation of q. So basically if I combine these two terms, I need to take the expectation only over x capital T given x0, and I have log of p x capital T over q x capital T given x0, okay, and I also have this term which I consider separately, okay. So that gives me expectation over q of x1 given x0 of log of p x0 given x1, okay, and then I have all these terms in the summation. So all these terms in the summation, okay, so what I do is that I actually reverse the order of numerator and denominator and write it with a minus sign. So there's a minus of t from 2 to capital T, expectation of q of Okay, so here I have xt minus 1 and xt, both these given x naught, log of q of xt minus 1 given xt and x naught over p theta t xt minus 1 given xt. Right. And this term is essentially the KL divergence between xt minus 1 given xt and x naught and xt minus 1 given xt. Okay, so this is the sort of KL divergence which is averaged over xt given x naught. Okay, and similarly this term is also the negative KL divergence between qxt given x naught and pxt, and this term is like a reconstruction term. So let's write them down all formally. Okay, so the first term we had was the negative KL divergence between qxt given x naught and pxt. So this is the prior matching term. So that is the posterior of x capital T given the data x naught and the prior of pxt, they should match with each other. The next term which we had was the reconstruction term, that I should be able to reconstruct back x1 from x naught. And finally, the remaining set of terms they are essentially the KL divergence which is averaged over qxt given x naught, and this KL divergence is between qxt minus 1 given xt x naught and p theta xt minus 1 given xt. Right. So essentially this is essentially the ground truth signal for denoising. So why I call it denoising is because the more closer to the data I have, the lesser the noise. So if we relook at this specific sort of graphical model, then essentially x naught is my data, okay, and xt minus 1 is always closer to data than xt. Okay. So essentially if I'm moving closer towards the data, I'm like moving it towards a lesser noise. And why I call it a ground truth signal, because it is also conditioned on x naught, right? Whereas this thing p theta xt minus 1 given xt, this is not ground truth. So this is essentially the trained denoising model. So there is a denoising model which we are training, and there is a ground truth denoising model which basically also has seen the data which is x naught. So this KL divergence term is sort of a denoising matching term. So it's matching the distributions of the two denoising counterparts. So this is the denoising matching term. Okay, so we have a prior matching term, we have a denoising matching term, and then we have this reconstruction term. So there are these three sort of terms which we have. So essentially we can try to optimize this sort of sum of all these terms, right? Because, and now the interesting thing is that this is expectation only over one latent variable which is xt given x naught, and then we have the this expectation is between is for the KL divergence between xt minus 1 given xt x naught and xt minus 1 given xt. Okay, so now the question is that how do I compute this particular quantity q of xt minus 1 given xt x naught? Okay, so let's try to understand that. So how do I compute this sort of posterior? Okay, so the solution to this problem is that I can write q of xt minus 1 given xt and x naught as q of xt minus 1 xt given x naught over q of xt given x naught, right? So we are just applying base rule, and this is nothing but q of xt minus 1 given x naught times q of xt given xt minus 1 over q of xt given x naught, right? So this is something which we have already defined, right? But these are the two terms which we need to compute. So we have defined q of xt given xt minus 1 as normally distributed with mean alpha t xt minus 1 and covariance 1 minus alpha t identity. Okay, so using this we can actually derive an expression for q of xt given x naught, right? And then since it's for generality, I'll also get the expression for q xt minus 1 given x naught, and then we can substitute them over here in order to get this distribution of q xt minus 1 given xt and x naught. Okay, so let's try to do that. So essentially the idea is that we know that xt given xt minus 1, okay, so this is normally distributed with mean root alpha t xt minus 1 and covariance 1 minus alpha t identity. Okay, so what I can write is that xt is going to be root alpha t xt minus 1, okay, plus 1 minus alpha t times this epsilon t star term, which is the sort of noise term over here, right, where epsilon t star is standard normal. Okay, so why we could actually write it in this form? Because essentially, so xt, if I condition it on xt minus 1, the mean is root alpha t xt minus 1, and so mean plus standard deviation times standard normal will give me this new normal distribution with mean mu and standard and basically covariance 1 minus alpha t identity, right? So actually it should be square root of 1 minus alpha t, right? Because the covariance is 1 minus alpha t, but the standard deviation is square root 1 minus alpha t. So now what I can do is that I can write xt as root alpha t xt minus 1 plus square root 1 minus alpha t epsilon t star. Now what I can do is that I can again apply the same expression again. So what we are going to do is that we are just going to proceed recursively down to x naught. So let's expand this term out for xt minus 1, and what I'm going to get is square root alpha t minus 1 xt minus 2 plus square root 1 minus alpha t minus 1 epsilon t minus 1 star plus square root 1 minus alpha t epsilon t star. Okay, and now what I have is that square root alpha t minus 1 xt minus 2 plus square root alpha t 1 minus alpha sub t minus 1 epsilon t minus 1 star plus square root 1 minus alpha t and epsilon t star. Okay, and now what I do is that I combine these two terms together. So this is the sum of two normal distributions, right? And one of them has variance alpha t into 1 minus alpha t minus 1, the other has variance 1 minus alpha t. So the total is going to be standard normal, right? And the variances and the means are going to be add up because these are independent random variables. Okay, so essentially this sum is also standard is also normally distributed with mean 0 and variance 1 minus alpha t minus 1. So just add the two variance term and this is what you're going to get. Okay, so essentially I can then say that, continuing, I can say that xt is going to be root of alpha t minus 1 xt minus 2 plus epsilon t minus 2 term, which is normally distributed with mean 0 and covariance 1 minus alpha t minus 1 times identity. And actually now I can just now substitute xt minus 2 in terms of its corresponding mean, which is alpha square root alpha t minus 2 xt minus 3, and then a noise term again. So continuing this in this manner, what I'm going to get finally is that this is essentially of the form of square root of alpha t up to alpha 1 x naught plus epsilon naught, and this is essentially normally distributed with mean 0 and covariance 1 minus alpha 1 up to alpha t. Okay, so this is what I'm going to get in the end. Okay, so here now we define alpha t bar, which is the cumulative alpha t, as the product of alpha 1 up to alpha t. So essentially xt is normally distributed with mean square root of alpha t bar x naught and variance 1 minus alpha t bar times identity, right? So therefore q of xt given x naught is normally distributed with mean square root alpha t bar x naught and covariance 1 minus alpha t bar identity. Okay, and you can also, like, if you have this expression for q xt given x naught, you have this expression for every t, which means that that also includes q of xt minus 1 given x naught. So overall the distribution of q xt minus 1 given xt and x naught is normally distributed So essentially what we'll need to do is that we'll need to again apply this particular base rule. Okay, so the one which we had written earlier. So this we know is a normal distribution, and this we'll also know is also a normal distribution, which we just derived. This is also we derived. So basically q xt given x naught is what we just derived, right? And substituting t equals t minus 1, we also have the numerator part. And substituting both of them, what you can show is that this is normally distributed with mean square root alpha t 1 minus alpha t minus 1 bar xt plus square root alpha t minus 1 bar 1 minus alpha t 1 minus alpha t x naught over 1 minus alpha t bar. This is going to be the mean, and the covariance is going to be 1 minus alpha t 1 minus alpha t minus 1 bar over 1 minus alpha t bar, this thing times identity. So you'll have to verify, okay, so you'll have to just substitute the expressions for xt given xt minus 1 and xt minus 1 given x naught and xt given x naught, and what you'll get is that you'll still get a normal distribution for xt minus 1, but the mean is now dependent on both xt and x naught, and the covariance matrix is independent of any of these xt and x naught. So this term I can also call as the sigma qt, right? This is the covariance term. So now the question comes up is that, how do we actually train the denoising term? So let's look back at the objective function we had. So if we have a look at the objective function, so here we had a prior matching term, we had a reconstruction term, and we had this denoising term. Right? So this prior matching term, that does not have any trainable parameters at all, right? Because pxt is just prior, and qxt given x naught also has all the fixed parameters. So basically this quantity does not have any trainable parameters at all. Okay. And if I look at the reconstruction term, that we already know how to sort of train from the usual VAEs, that given x naught I can sample x1 and then I can try to reconstruct back x naught, and that will give me the reconstruction term. Again, we can use the reparameterization trick to back propagate, so the sampling step. Now we come to this particular set of terms which form the denoising term. So how do we now try to optimize this thing, right? So basically, if we are maximizing this objective function, since this KL term comes with a negative sign, we'll try to minimize this KL term. And if we try to minimize this KL term, we need to bring this distribution P and Q close to each other. So for this distribution Q xt minus 1 given xt and x naught, which is the ground truth denoising signal, we have computed the form, right? So this form is essentially a normal distribution with this form of means, which is of some function of xt and x naught, and this particular covariance matrix, which is independent of xt and x naught, right? So Q of xt minus 1 given xt and x naught is a normal distribution with some mean, which is a function of xt and x naught. So this function is this particular expression. It's some linear combination of xt and x naught, and the coefficients come from hyperparameter and some coefficient and some covariance matrix sigma qt, which is essentially a diagonal matrix, which is a multiple of identity, and it does not have any parameters xt and x naught at all. Okay, so now what I want to do is that I want to define this distribution p theta xt minus 1 given x naught, which is as close as possible to this distribution q, right? And so since we know that the original distribution is a normal distribution, so we can also consider this to be a normal distribution, right? Because we want to find the best the closest distribution to q xt minus 1 given xt and x naught. And now this is going to have some sort of mean, but the thing is that this particular mean mu theta can only depend on xt. It does not see the ground truth signal x naught. Okay, and it depends on xt, and since basically we want one neural network to define it, so we are also going to have a time step encoding t in it, right? Because this the network is common across all time steps, but I just sent encoding for this particular value of time. And the covariance matrix for this is what I'm going to characterize by sigma qt, which is the sigma q square t, the variance times identity. Sigma q square is what I have over here. Okay, so I already knew that the correct distribution has this form of the variance, so let me use that. And now what I need to do is that I need to find the mean which minimizes the KL divergence, right? And if you try to minimize the KL divergence between two normal distributions which have the same covariance matrix, right? So this is equivalent to, so minimizing KL divergence is equivalent to minimizing the square norm difference between the two means. So between mu theta x tt and mu q xt and x naught. So minimizing this sort of square difference is is equivalent to minimizing the original KL divergence term, right? So basically the thing is that for every t I need to have a neural network which is able to output the expected value which is close to the original mu q, right? The expected value when it sees the sort of x naught as well. So of course we can always try to do this thing, but then an interesting idea is that well, I also have the form of mu q, which is essentially a linear combination of xt and x naught, right? And these coefficients are something which I already have, right? These are just the hyperparameters. So what I can do is that I can also try to model mu theta in the same formulation, right? So model mu theta of xt and t as square root alpha t 1 minus alpha t minus 1 bar xt plus square root alpha t minus 1 bar x theta hat xt and t. So essentially this mu theta, in order to compute this mu theta, I need to get some approximation of x naught, which is going to be given by x theta hat over 1 minus alpha t bar. Right? So essentially now if I want to minimize, okay, so the reason why I choose this particular formulation is because in the original value of mu q I had the same thing, except here I had access to the ground truth which was x naught. Here we do not have that, but now I have a neural network to predict x naught. And the square difference between mu theta and mu q, minimizing that, this is equivalent to minimizing x theta hat xtt minus x naught square, right? So here essentially what we are trying to do is that we will try to recover x naught from xt. What we can do is that we can use the same network along with the time embedding. And we'll use that to like basically we are going to use the shared set of parameters, and then we'll pass in the value of time, and then we'll try to predict x naught. So basically at time t I have this network, so this is some feed forward network which takes as input xt, and it also takes as input an encoding for time, and then it tries to predict x naught. So it tries to recover this x naught. Okay. So the idea is that now it looks very similar to VAE, except that at for every time step t I try to recover back my x naught. And this particular network which we'll have is essentially estimating the value of x naught, but this linear combination is what's the is how this expectation is how it is going to approximate the mean of the distribution. The covariance is something we already know. Okay. And now actually if we look at the expression for xt given x naught, which was normally distributed with mean square root alpha t bar x naught and covariance 1 minus alpha t identity, right? We can say that xt is going to be square root of alpha t bar x naught plus 1 minus alpha t bar times epsilon naught, or x naught, if I just take x naught to the other side, I'm going to get x naught is xt minus 1 minus alpha t minus 1 bar epsilon naught. So here essentially this epsilon naught is going to be my noise term, right? Okay, actually it should be a square root over here. Okay, alpha t bar. So essentially we are using that again, that sort of reparameterizing idea, that if you have some normal distribution which is of this form, then I can write it as the mean plus the square root of the covariance matrix times epsilon naught, where epsilon naught is a standard normal variable. So this is the noise term, right? So you can think of it this way, that x naught was my original image, and I apply some rescaling, and then I have added some noise which has given me this xt. And now in order to recover back my original image x naught, I need to subtract the effect of that noise and also rescale it appropriately. So when we are trying to minimize sort of this the difference between x theta hat and x naught, right? So as we said over here that when we are parameterizing my mu theta as a linear combination of xt and x theta hat, where x theta hat is trying to approximate x naught, then essentially what we can do is that we can even model x theta hat as also of this form. One minus alpha t bar times some epsilon theta hat over square root of alpha t bar. Right. So here essentially what I have said now is that my x theta hat is going to be xt minus some expression for this noise and then rescaled appropriately. Okay. So now minimizing the difference between x theta hat and x naught is equivalent to minimizing the difference between this approximation to noise and this original noise, right? So given xt and t, I try to recover back my noise, okay, which is epsilon naught, and this is how I'm going to approximate it, and therefore basically this is equivalent to learning the noise given xt and t. Okay, so essentially we started with this particular sort of formulation for this variational diffusion models, wherein we have x capital T, which is normally distributed, and conditioned on the previous latent variable, we have the new latent variable. And in variational diffusion models, the assumption is that the specific form of the posterior is again a normal distribution with mean as root alpha t xt and covariance as 1 minus alpha t I, right? And once we had that particular form, we tried to compute the ELBO. And when we tried to compute the ELBO, one idea was that we directly combined the terms from numerator and denominator, but that led to a term with a high variance. In order to reduce the variance, we actually wanted to split the expression in a different manner. And when we actually splitted the expression, we had actually gotten these form of these terms, wherein we had a reconstruction term, we had a denoising matching term, and then we had a reconstruction term, a prior matching term, and denoising term. The prior matching term does not have any parameters, whereas this term had the reconstruction term and the denoising matching terms had their specific parameters. But now we have seen that for this particular reconstruction term, we can use the VAE formulation. But even for other terms, we have seen that a formulation which is very similar to VAE suffices. That is given. So I write the expression for normal distribution, where I need to estimate the mean and the sort of covariance. The covariance is something which I already know. I have the form and I have the correct form which is coming from this ground truth signal. And now what I need to ensure is that the two means for these two distributions are close to each other. Since the mean for the original value of q is a linear combination of xt and x0, I can take the form for p theta also in similar manner, but now I do not know x0. So basically one interpretation was that I tried to recover back my original image, which was x0. But since x0 can be expressed in terms of xt, wherein I have subtracted the noise term, I can also equivalently consider it as the problem of predicting noise from the value of xt, right? And when I have the sum of all these terms, I can also consider this as some multiple of the expectation, wherein I have sampled t from 1 to capital T, and then for that particular value of t, I try to minimize the scale divergence. Okay, and actually this particular term can be written it as a negative of the scale divergence between q and p x0 given x1 up to a constant, additive constant, right? So that additive constant is going to be of the form like q log q, so that wouldn't matter. So I can actually combine all these terms in this sum of these scale terms. And now the algorithm is that I sample an index, then given the sort of image, I try to get back the value at xt. And then from that xt, I try to recover back the image, or I try to recover back the noise, right? So this is how the algorithm is going to work. And for coding part, I'll actually put some links in the description box, which basically show that how you can implement this particular algorithm. But the proof and the mathematical formulation is what I wanted to cover in this series of lectures which we have discussed today. Okay. So yeah, thanks a lot. Hope you liked these lectures. Yeah, so the coding I haven't implemented myself, but there are other good GitHub repositories and coding tutorials for this thing. So I'll just point you to those. Okay, thanks. Bye.